Hey everybody, it's Mr. Eisens here, and we are in part 2 of the 8th grade STAAR review. We're going to be going over force and energy and motion. All right, so again, this is a review of everything that we've learned in 8th grade up to this point, and we're just recovering basically our physics section and everything that we should know and be able to answer. So we're going to go through a few questions. Make sure you pause the video, try to answer the question yourself, and then continue reviewing with me. And we'll just practice these questions. If you find stuff that you're not good at, or you know you got wrong, you know that might be something that you want to review more later. So good luck, and let's get going. Okay, so physics is a lot of math. Luckily, the math is all within formulas, okay? And you're given a formula sheet. So if you can identify the correct formula to use and what units give you which parts of the formula, so force equals mass times acceleration, well, force is usually measured in newtons, mass is usually measured in grams, okay, and acceleration is measured in meters per second squared, then you're able to kind of match them all up. So the golfer hits an orange golf ball with his golf club. The golf ball has a mass of 0.08 kilograms, and when it was hit, it accelerated 1,500 meters per second squared. What was the force used to cause the ball to accelerate? So, what are we solving for? Well, sorry, we got to do our net force calculators. So, we got to decide when we look at arrows what we got to do. So, when arrows are going against each other, they're actually going to cancel each other out. Okay, cancel each other out, and so we got to subtract. So again, they're headed in different directions once again. Therefore, we gotta subtract. Okay, their overall numbers. So the second example would be like tug of war. Okay, up versus down, they're going against each other. So subtract again. Now we got to add when they all go together. All right. So unbalanced force in motion. This is called acceleration. It's hard to read right there, but it's acceleration. Okay, it's a change in speed. All right. If you go the same exact speed, you're not accelerating. All right. I guess we're going to start at the bottom. Okay. So tennis player hits a tennis ball with a force of 10 newtons. The ball has an air resistance force of 0.7 newtons. What is the net force acting on the tennis ball? Well, okay, the tennis ball is being hit with the person with the tennis ball or person with the tennis racket. Okay. And then the air is the resistance. And so that is going in a different direction than the so the force of the tennis racket hitting the tennis ball, 10 newtons, the air resistance going against it. So you got to subtract 10 minus 0.7 gives us 9.3 newtons, which makes sense because the tennis ball should be going at a pretty decent speed after it gets hit. All right. Okay, what are we solving for? We want force. Finally, we're back to the problem I thought we started with. Okay. So back to our golfing example, we want force. We've been given the acceleration and the mass. Okay, so in F equals ma, all right, the formula that we're using, we identify both of our variables, 0.08 and 1,500. We put them into our equation. 0.08 times 1,500 is going to give us 120. And then we need to remember the units. The units for force are usually newtons. All right. All right. Lastly, we're going to be talking about this kayaker. Okay, the water has a current of 5 meters per second squared flowing southeast. Okay, so this would be a good example to write something down. All right, so southeast, if we use our pen, southeast is going to be at an angle right here, down and to the right typically. All right, the kayaker is resisting the current by dragging the paddle he is using, since the kayaker is applying an unbalanced force. So he's getting dragged this direction, and he is dragging. So he's actually going to go against that force. All right. So drawing a little force diagram like this is going to really help you. Dragging the paddle. Since the kayaker is applying unbalanced force with the paddle, what is going to happen to the kayak if he only applies a resistance force of 3 meters per second? So he's got 3 this way, and we are going to have 5 going this way. So our overall answer, once we get back to our marker, okay, he's going to slow down. And then if you were to do the math, he should have about 2. So let me just go back to pen, clear the screen, and then back to our mouse again. All right, so now we're going to talk about speed and acceleration. So speed is the measurement of rate of change of position with respect to time. So it's distance over time. How far do you go and how fast do you do that? Okay, a 40-meter dash, okay, or 40-yard dash. You go 40 yards, and how long does it take you to do that? That's how fast you are, okay? Acceleration is your change in an object's speed and direction. It's got to be direction, okay? So you can go the same speed, but you can turn, okay? Because you can have your car on cruise control, but then you hit a bend in the road, and you can feel yourself being pulled off to the side of your car, all right? Because you're feeling the acceleration, all right? So speed and direction. Make sure you remember that. Okay, velocity is going to be the measurement of speed and direction of an object. So it's the only difference between speed and velocity is all of a sudden with velocity, we say we're going to head north, south, northeast, west, east, any of those directions, okay, toward the school, away from the school. As long as it gives you any direction, you're good to go. All right, so let's move on and see if we can answer some questions. If a motorcycle racer is traveling a speed of 16 meters per second, okay, around the track, the rider is going around a curve. Now explain why the rider is changing velocity if speed stays the same. Okay, if you're going around a curve, you're changing directions, okay, and so his velocity is changing. The direction he is headed is changing. All right, a meteor is moving at 442 kilometers per minute, traveling in a south to north direction. Okay, direction passed the Earth in 1999 because the meteor was only 34 meters wide and was 25,600 kilometers above the Earth's surface. It was not visible without an aid of a telescope. What describes the meteor's motion? Okay, so what would describe its motion? Well, it's headed from south to north, so it's headed 442 kilometers per minute. You could change that to seconds if you wanted, and then it's headed northward. All right, so let's see. So our motorcycle example, it's changing direction to go around the track, and then the meteor is 442 kilometers per second. This is actually a little bit wrong because 442 per minute is what it says in the question. So you'd actually need to calculate and multiply by 60 in order to get your actual kilometers per second northward. All right. So now let's talk about the different laws of motion, Newton's laws. Okay. So Newton's first law. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion, okay, unless acted upon by an unbalanced force. So my pen, when I set it down and I don't act on it, is going to stay there because the forces are unbalanced. But if I act upon the pen and push it to bring it upwards, it is going to be in motion now. When I throw it, okay, the pen will stay in motion until it is acted upon by another force, until it hits the ground and it comes to a stop. All right. So basically, things tend to do this. Something that confuses us sometimes is gravity. Gravity's always acting on us. All right. And so what's nice, though, is when we have all the information, as in Law 2, where we actually get our equation of force equals mass times acceleration, okay, F equals ma. All right, now we can kind of get a better idea of how objects are going to, we can predict what they're going to do, all right, and how they're going to do it. And so force equals ma is really, really important to us. Make sure to use your equation sheet and try to identify anytime you have numbers, is this a force times mass, or a force equals mass times acceleration question? Okay, Newton's third law is every action has an equal and opposite reaction. Okay, so for example, if you are sitting or standing right now, as long as you're not in motion, okay, you are at rest. Your force that you have, so right now I'm sitting in a chair, okay? The force that I have, my body weight, okay? Gravity is pulling down on me, all right? So here's my picture of my chair, okay? And there's me, okay? I have really short legs. I'm not a very tall person. So my force is headed down like this. But because the chair is there, gravity is acting upon me. And so the chair is actually pushing on me to hold me in place. If the force was unbalanced, if the chair could not hold my weight, the chair would break. All right. And then the floor would hold me. All right. So whether you're standing, whether you're sitting on a chair, okay, there's always forces acting on you because gravity never stops when you're on Earth. All right. And so the equal and opposite force is the ground holding you up, okay, or the chair in this case. All right. And then luckily we have our bones and our muscle to help support our body and keep it in the orientation we want. All right. So just keep that in mind as we move forward. It's something that you really got to just think through. All right. For every action, there's an equal and opposite reaction. Okay, so let's think about some of these. All right, a skater applies an unbalanced force of 50 newtons to propel himself. What is the mass of the skater if he accelerates 0.8 meters per second squared? Okay, so this is a force equals mass times acceleration problem. All right, so what are we solving for? We want the mass. It asks for the mass. What's the formula we're going to use? Force equals mass times acceleration. Perfect. What do we have? We have the force calculation, which is 50 newtons, and we also have acceleration. Okay, so we're going to have to do a little bit of math to figure out what our equation is. As you can see, we have mass times 0.8 is going to give us hopefully 50. But in order to figure this out, we got to do 50 divided by 0.8. Okay, and that's going to give us 62.5 kilograms. That is a pretty heavy skater. All right, actually not that bad. It's actually not that bad. That's probably one of you guys. I want to say I'm about 100 kilograms. I could be wrong there. And I'm like 190 pounds. Anyways, I want you to think about this problem again, though, because this example of the skateboarder could easily be Newton's third law, because every time the person pushes on the ground pushes back on them. That allows them to push them forward and propel them forward. Okay, and so every situation you can think about all three laws and kind of apply them in some way. Okay, if the person doesn't push themselves at all and they just stand there on the skateboard and they don't move, then it would be an object at rest stays at rest, right? So you can kind of think about them in multiple aspects in multiple ways. Okay, the aerial artist pictured is experience Newton's third law. Okay, third law, remember that's equal and opposite. Every action has an equal and opposite reaction. Okay, describe the action-reaction pair she's experiencing. So she is just holding on to two ropes or holding on to a rope. Okay, she's a tightrope walker. All right, and so her force is going down on the rope, but also the rope is pushing back on her. All right, so let's see what they say. The body is pushing down on the rope, and the rope is pushing back on the aerialist. Perfect, we got it. Which of the following scenarios is experiencing unbalanced force? A ball rolling at a constant speed. Okay, it's rolling at a constant speed, so it is going to be actually a balanced force because it continues going at a constant speed. An apple hanging in a tree. Again, it's not moving, it's just staying there, and so it should be a balanced force. Okay, a trophy sitting on a shelf, not moving, once again, unbalanced. It should be balanced. A truck traveling at 75 meters per second. As long as it's going at a constant speed and it's not changing direction, because if it's changing direction, then it's actually accelerating. Okay, so that one should be a constant or a balanced force as well. And then a playground swinging back and forth. Okay, now we're going to have an unbalanced situation going on because it's changing speed, it's accelerating, it's slowing down, it's also changing direction. Okay, there's a lot of unbalanced forces going on there. All right, let's keep on going. So school bus is traveling 50 kilometers in 30 minutes. What is the average speed of the bus in kilometers per hour? Okay, So we have it in minutes. We want it in hours. That's something you got to identify. All right. Make sure your units are correct. So luckily, minutes to hours, there's going to be 60 minutes in an hour, and 30 is half of that. So you can actually just multiply times 2. All right. So a school bus is traveling 50 kilometers in 0.5 hours. All right. So this is speed is equal to distance over time. We want the average speed. All right. So we should get 25, okay, as our kilometers per hour. Okay. 50 times 2. Okay. It's a little bit confusing. Oh, okay. Yeah, they multiplied it by 2 because it's 0.5. So you could divide by 0.5 because that's the same as multiplying by 2. All right. So 50 divided by 0.5 gives you 100 kilometers per hour, just as 2 times 50 over 30 gives you 100 kilometers per hour as well. So it's up to you how you want to do your math. I would have divided by 0.5, but you could just double your whatever you get from using your other units. Okay. What is the average speed of the rabbit during the time represented in the graph? So the motion of the rabbit, we have a distance versus time graph. Oh, these are like my favorite. I love these graphs. Okay, because they tell stories. All right, so basically what we can tell from this graph is right away the rabbit is at distance 0. After 20 seconds, the rabbit's traveled 2 meters. Okay, and then after 10 more seconds, the rabbit has jumped and traveled all the way to 6 meters. And then after 50 seconds, the rabbit's traveled 10 meters. All we care about for average speed is the entire distance. So we really don't care about we just care about the total distance that it traveled in the amount of time given. All right, so what is the average speed of the rabbit during the time represented in the graph? Well, it ends at 10 meters, and how long does it take? 50 seconds to do it. So 10 meters divided by 50 seconds gives you 0.2 meters per second. All right, even though the rabbit was much faster for 10 seconds in the middle, okay, because the slope is higher, it's steeper, okay, it's going a lot faster. For average speed, it doesn't matter. Okay, a baseball player is working on his batting skills. He hits a baseball 3 times, and another player records his data. How long did it take for the baseball to travel 378 feet? That's a bomb, by the way. That's a big hit. That's a home run in a lot of parks if you hit it down the line. Okay. Anyways, so we got this one went 369. The time took 3.45 seconds. Again, we're given the distance, we're given the speed, and now we need to calculate time. So speed equals distance over time. What are we solving for? Well, we're solving for time. So we're able to plug it into our equation. Okay, speed equals distance over time. So we just divide we're going to multiply speed times time. And it's going to give us, sorry, we're trying to solve for speed. So, whoa. No, we're good. So speed, distance over time, we were trying to solve for time. So we got to multiply by time and then divide by speed. Yeah, okay, we're good. So we're taking, you got to shift this equation around. So we get rid of the t, we multiply t to both sides, we get rid of the t, and then we divide by the s. So we have distance divided by speed is going to give us 3.41 feet per second. All right, moving on. Okay, we're telling stories again. Okay, you got to think about conceptually what is going on. All right, if you have a flat line, it is at whatever distance this is, and it's not changing. All right, so it is, you got to think of it as a motion sensor is recording you, and the distance that you are away from it doesn't change. All right, so let's say this is 20 meters away from the motion sensor, and you don't change distance. Well, you're not moving then. You're staying still. So you're not moving at all. Okay, so you're standing still. Any flat line, 0 slope is going to be standing still. Okay, you're moving. Now you have a consistent slope where you're changing distance at a constant speed, okay, because the slope is changing. So this is just, you're moving away from the motion detector at a constant speed. Okay. Over here, you have a curved line. This means you are speeding up. You are speeding up. You are accelerating, and you are running, okay, away and getting faster as you do it. All right. Here, the opposite, you would be slowing down. You would be decelerating. So negative acceleration. All right. So not moving, constant speed, speeding up, slowing down. A car left its house, traveled down the road for 4 miles, stopped at a red light, continued to drive to the store, and went shopping, and then returned home. So let's just think about this before we write it. The car traveled down the road for 4 miles. Okay, so it's probably moving at a constant speed, and it's got to reach 4 miles. All right, it stopped at a red light. So it stopped for a little bit. All right, it was not moving. Continued to drive to the store. So it should continue at that same speed or very similar. Okay, once it gets to the store, okay, went home and then went shopping and then returned home. So the car then had to stay in the parking lot, and then they returned home. So they're returning back to the beginning. So they're headed back the other direction. All right, let's see if we can match something like that. Oh, clear the screen. Let's get this. Okay, yep. Perfect. We got it. Good job, guys. All right. Let's keep going. Oh, that's it. That's it for the Newton's laws and physics. So if you have any questions, make sure to ask your teacher or find me at some point, and we can talk some physics. But otherwise, good luck on STAAR, guys. I'll see you later. Peace.